Hey there, everybody. Welcome back. This will be the second of 3 videos for 13.1 in Calculus 3. We are in multivariable functions again, and we're looking at contours. So to lead into it, I'm going to start with the example f of xy equals the square root of 16 minus x squared minus y squared. What we're going to do is let z equal f of xy, and we're going to figure out what we get. So we could square both sides and collect all the variables on the left side. We get x squared plus y squared plus z squared equals 16. This would be a sphere of radius 4, but since f of xy was the square root, it's just the positive half. There's no negative z here. So we get a picture like that. And that's old. We did that in chapter 11. But what happens if we look down on it from above? If we look straight down the z-axis, we get this, it looks like a circle, but this is a lot like looking down on terrain in the, like from over above in a plane or a helicopter. And we get like a map. We can make a map of like contour lines. So contour lines are areas where the elevation has the same height. And so we draw a line of where the elevation has the same height. And so mountaintops have very small little lines because it's not a very big thing, but big wide regions of flat land will have a big area of circle. So to illustrate this, I'm just going to plug in z equals 0 through 4 and show what we get when we do it, and then we'll map out the contour lines. Okay, so if z equals 0, we have 16 minus x squared minus y squared equals 0. So 16 equals x squared plus y squared. It's a circle of radius 4. So when z equals 0, we're going to have a big circle, radius 4. When z equals 1, we have 15 equals x squared plus y squared. So it's a radius of square root of 15, which is about 3.87. It's just a little bit smidgen smaller. And we can see that if we look on the graph, like going from x equals 4 to z equals 1, it doesn't start curving in and getting very narrow up there. So like this part right here isn't much narrower than that ring right there would be. So it's not very much. You will see on the contour lines. If we do z equals 2, z squared is 4. So we have x squared plus y squared equals 12. 16 minus 4 is 12. The radius there is 3.46. We're getting a little bit smaller, but we're not there yet. Z equals 3. 16 minus 9 is square root of 7. 2.65, well, that's a good jump. So when we went from z equals 2 to z equals 3, up on here on the graph, it's right about. So like here's 2. 3, notice it starts getting pretty narrow. We can noticeably see that the part it's going in is getting bigger. And here it's getting even bigger. So I'm guessing when we get up a little larger, we can see it getting even tighter in. The z equals 4, of course, is 0. So when I graph these circles, I get this. The outside circle is z equals 0. That's the red one. Z equals 1 is just barely inwards. These are terrible circles. Make fun of this one too, Ben. Just a little tiny bit inward. 4 to 3.87 isn't that much of a reduction. Going into 3.46 is a little bit more noticeable. If we go into z equals 3 at the 2.65 radius, we get that. And z equals 0 is pretty small. What happens if we do z equals 3.5? 16 minus 3.5 squared equals, and we take the square root of that. So 3.5 is at like 1.93. We could put that right here. 1.93 is close to the 2. And so I'm just drawing the values like that. So the higher elevations have smaller areas on the contour because there's less values at that higher elevation. And this is kind of like how contour maps look. So we could look at some contour maps. Contour. Let's see, do we have the San Joaquin Valley? That doesn't show the contour map. I'll go back to what we had before. Sometimes I'd like to use color for it to show heights, as we can see here. They'll use color to illustrate the different dimensions or the different contours. But when you're not drawing with color, you kind of got to do, let's get back to where we were. You get things like this. And they will notice how, let's see if I can zoom in for you. That's not helping. Open up that picture real quick. So a topography map or contour map. Along the lines, they will generally show a number on the line to show what the elevation is there. I didn't do that on mine. I showed it next to it with an arrow pointing because it's a little harder to read. But that's how they do contour lines. So let's take a look at a different way of looking at contour lines without a graph. Like that. So we didn't have a function for this one right here. I just drew like a mountain range kind of image right there. It's of course a little cartoony for a mountain range because it's not jagged or anything like that. But what you do is you just make lines as you're going up and you depict them below. So the green circle, k equals 0, is pretty big. And there's no interruptions. K equals 1 and 2, also good size, but notice that the k equals 1 is a little bit narrower than k equals 0, and k equals 2 is also a little more narrower. So we show them going inward like this. K equals 3, we start interrupting. There's a gap right here for this little dip. So we have to have 2 separate regions for k equals 3. K equals 4 is just on the left region, so we don't have one in the right. And we illustrate it there. And then finally at k equals 5. I was just using k. You could say z or h there for height. But that's how we do contour lines and how to read them. So translating, you can go the other direction. You can go, okay, I got a big thing right here. I'm going to have a couple peaks here because there's small circle here. Small circles here. This one looks like it gets a little bit higher than this one because the number is larger for it. It says k equals 5 here. This line says k equals 3 here. So this left peak is higher than this peak. Okay, peace.